So last time we proved Sylow's first theorem, which essentially states that if G is a group of order p to power alpha times m, where p is some prime not dividing m, then G contains subgroups H of order p to power k, where k ranges from 0 to alpha. And those subgroups are called P subgroups. And the highest power of them, the one with p to power alpha, is called Sylow P subgroup. And the last proof essentially entails that the set of all Sylow B subgroups, which we denoted by Sylow P of G, is non-empty. It contains at least one Sylow P subgroup. And on the left here are some of the tools and concepts which we used along the proofs. And here is our friend Mr. Sylow. This time we are going to prove Sylow's second and third theorems, essentially completing all the three theorems. But before we state and prove the theorems, we just prove a small lemma, which is going to be useful in both cases. So we start with a lemma. This is really a general lemma related to group actions. So it says, let G be a group of order p to power alpha. Okay, alpha is just non-negative integer acting on a finite set S, just some finite set S, and then let we take just a subset of S naught be the set of all elements in S, so the set of all elements A in S, which is fixed by the group G. So that is all sets A such that little g dot A equal A for all G in the group G. Okay, and this dot here is a dot of the group action. Okay, then what happens? We have the following. The size of the set S is congruent to the size of the set S naught mod B. Now, the proof of this is really short and simple. We just need to recall few facts from group actions. So I will just draw it on the side here. Okay. So first, remember that when the action of G is applied to the set S, it creates an orbit around the elements of S. And the orbit of an element A in S is all elements B in S which are related to A through group action. So this means there exists some little g in the group G where G dot A equal B. Okay, so G here is in the group G. And second, when the action is applied, it partitions the set S into disjoint orbits. So if we have our set S here, and here are the elements in S. Okay, so applying the action creates disjoint orbits. But it might be the case that for some elements there is only a single element in the orbit. Okay, and this is specifically the case where G dot A always equal A. This is for all little g in the group G. But this is nothing else than our subset S naught, because by definition S naught is all elements in A where the action applied to the elements give again the same element. So in fact, we can divide the set S into two big subsets, one containing the orbits which are having more than one element, and the second contains orbits which are having only single element. So here we have single element, and this is S naught. Okay, and this is S minus S naught. Third, remember from the orbit stabilizer theorem, we have the size of the orbit over any element is the index in G of the stabilizer of the element in G. And the stabilizer of the element in G is a set of all little g in the group which are fixing this element. So G dot A again equal A. And this is, of course, a subgroup of the group G. Okay. Now, we can write, starting the proof, we can write the size of the set S as the summation of the size of all orbits. Okay. But for each orbit, we only need to take representative from the orbit. We do not need to consider all the elements. Otherwise, the size will just got duplicated. So to do this, we can just create a subset of S which contain single element or single representative from each orbit. Okay. So here A belong to L. This is some subset of S. Again, this can be rewritten as the size of S naught, if we just take the size here, plus, so this is the size of the orbits in S naught, plus the size of the orbits outside S naught. So here A belong to L minus S naught. Okay. And this itself equal the size of S naught plus summation, and from orbit stabilizer theorem we can replace the size of the orbit by the index in G of the stabilizer of A. Again, A is in L minus S naught. Okay. Now here is the important point. You note that the stabilizer in G cannot equal the whole group G for all elements A in L minus S naught. So for all elements here in this part, the stabilizer cannot equal the whole group. And the reason is that for the elements in this section, there must exist at least one G such that G dot A does not equal A. Because if G dot A equal A for all elements G in the group, then we end up here in this section where we have single elements in the orbit. But we are here in this section, and this means we must at least have more than one element in the orbit. So this means this stabilizer cannot equal the whole G. Okay, cannot equal the whole G for only A in L minus S naught. Okay. Now this implies the order of the stabilizer does not equal the order of G. Okay. Now again we have here the size of S equal the size of S naught plus the summation, and we can write this index as the order of G over the order of the stabilizer of A. A is in L minus S naught. Okay. Now we're almost done here. So since the stabilizer of A is a subgroup of G, this implies the order of the stabilizer divides the order of G. But the order of G is P to power alpha. So this implies the order of the stabilizer divides P to power alpha. And since we have shown that the order of the stabilizer does not equal the order of G, this implies G, the order of G divided by the order of the stabilizer, which is P to power alpha by the order of the stabilizer, is equal B to power alpha minus some J. This is some natural number J, okay? Because this, the order of stabilizer divides the order of the group. And now we can write the size of S, which is the size of S naught, plus the summation order of G over the order of the stabilizer. We can write it as follows. So this equal the size of S naught plus B. We can take B out from each term here. Okay, so B multiplied by the summation of P to the power alpha minus J minus 1. Okay, where J is just some natural number. Okay, now finally, when we take mod B on both sides, all of this goes to 0. Okay, so we end up with the size of S is congruent to the size of S naught mod B. Okay, and this completes the proof of this important lemma. Now we can move ahead and prove Sylow's second theorem. And the statement of this theorem reads as follows. If G is a finite group of order B to power alpha times M, where B is some prime not dividing M, then something interesting happens with the Sylow B subgroups. Then any two Sylow B subgroups are conjugate. And this is called also the conjugacy theorem. So in the first Sylow theorem, we proved that the set of Sylow B subgroups is non-empty. It contains at least one subgroup. And before we go into the proof, let's just conceptualize what this means. So if this is a set of all Sylow B subgroups, which is the subgroups H of G, such that the order of H is P to power alpha. This is the Sylow B subgroups. Then any two subgroups H and Q in this set are conjugate, meaning there must exist some element G in the group G such that H equal GQ by G inverse. Okay, and furthermore, if you take the subset, the all subgroups of G, we take it with this color. This is all subgroups of G, and if the Sylow B subgroups are made with some different color. Then we apply an action of G by conjugation on the subgroups. So the action would be G dot H for any subgroup H equal G H G inverse. Then when this action is applied, it will partition the subgroups into disjoint orbits. What is interesting here is that all Sylow B subgroups will fall in the same orbit, because we can obtain any one of them from the other by just conjugation, and all the others will fall into some other orbits. Okay, so this is the meaning of this theorem. Now we can go to the proof. So proof, we start by taking two Sylow B subgroups. So let H and Q be in the set of Sylow B subgroups of G. Okay, and let S, let's define some set S to be the set of all left cosets of H in G. So this is the set of G H little g such that G is in the group G. Okay, and as you may expect, we will apply some group action on S, but this time we will not apply action of G. Instead, we will apply action of Q. So let Q act on S by left multiplication. That means by for all little q in Q and G H in S, the action is defined as follows. So Q dot GH equal QGH. Okay, so this is the group action we are going to use, action by left multiplication. Now we define our S naught. Let S naught equal the set of all left cosets GH in S such that GH is fixed by all Q elements. So such that Q dot GH equal GH for all Q in Q. Okay. Now remember from the lemma, we have the size of S congruent to the size of S naught mod B. This is where the lemma comes to play its role. Okay. Now, since S is defined to be the set of left cosets of H in G, then we also have the size of S equal the index of H in G. This is Lagrange's theorem. And in turn, this equal the order of G divided by the order of H. Now, what is the order of G? From our definition, the order of G is B to power alpha times M, and H is a Sylow B subgroup, which means its order is B to power alpha, so this gives us M. Okay, so in conclusion, the size of S is just M. Okay, now since the prime number B does not divide M, then this implies B does not divide the size of S. But this also means that B cannot divide the size of S naught, okay? Because the size of S is congruent to the size of S naught. So they are always divisible by the same numbers, okay? So this implies B does not divide the size of S naught. And therefore, the size of S naught cannot be 0, okay? So S naught contains some elements. So S naught here contains some left cosets of H. Now we can take one of those left cosets. So let GH be in S naught, okay? Then by the definition of S naught, we have the following. We have Q dot GH equal GH for all little q in Q, okay? Now the action of Q gives us the following. This is by the definition of the action. From here we have Q G, then H equal GH for all little q in Q, okay? And then just multiplying both sides by G inverse results in G inverse Q GH equal H, again for all little q in Q, okay? So this is valid for all Q, for all the subgroup Q, which implies that G inverse the subgroup Q itself by G is a subset of H, or we can even say it is a subgroup of H. So this is point 1. And from the other hand, we have the order of this G inverse Q. G is the same as the order of Q because the conjugation does not change the number of elements. Conjugation, left multiplication or right multiplication, all of them does not change the number of elements in the group. And the order of Q is the same order of H because both are Sylow B subgroups of order B to power alpha. So we obtain the order of G inverse Q. G is the same as the order of H. This is 2. So we have two subsets of the same order, but one of the subsets is contained in the other. This only happens if the two subsets are the same. So this means that H equal G inverse Q G, which means H and Q are conjugates. And this completes the proof of the second Sylow theorem. Now we move to Sylow's third theorem, and this is also called the counting theorem. And we will see in a minute why it is named counting theorem. So the statement reads as follows: let G be a finite group of order B to power alpha times M, where as usual M is not divisible by B. Then the number n sub B, okay? This is the total number of all Sylow B subgroups in G, of Sylow B subgroups of G is the number 1 plus k p, where k is some non-negative integer. Okay, and furthermore, this number n sub b divides m. Okay, in some text you will find it n sub b divides the order of G, which we will show it is in fact the same thing. Now the proof is very similar to the proof of the Sylow's second theorem, and in fact we will employ very similar techniques. So proof, okay, we will define this time the set S. So let S be the set of all Sylow B subgroups of G, and this means that S equal the set Sylow B of G. Okay, and let's take just any particular subgroup in S. So and say Q is in S. Now we apply a group action of Q on S, and this time by conjugation. So let Q act on S by conjugation. And what this means, for all little q in Q, and if we take any, let's say H in S, then the action is defined as follows. So Q acting on H equal Q H Q inverse. Okay, so this is an action by conjugation. Right, now we define our S naught. So let S naught be all subgroups in S which are fixed by the action. So S naught is all H in S such that Q dot H equal H. This is for all little q in Q. Okay, and this also equal H in S, and this is an action by conjugation. So QH Q inverse equal H for all Q. Okay, now you will notice that in this definition the set Q itself, or the subgroup Q, must be in S naught, and the reason is that for this definition we always have Q little q by Q, then Q inverse equal Q. This is always true since little q is in Q. So S naught is non-empty. Okay, so since Q is in S naught, then S naught is non-empty, and therefore we can consider elements in S naught without a concern that S naught will have no elements. So let's take a subgroup in S naught. Let H be in S naught, and this means that H equal Q H Q inverse for all little q in Q. This is just by the definition of the subgroups in S naught. Now we look at the normalizer of the set H. Remember that the normalizer of H is all x in G such that H equal x h x inverse. Okay, and it seems clear from here that all this q must be in the normalizer of h, just by the definition of the normalizer, and therefore q itself is a subgroup of the normalizer of h, because the normalizer is also normalizer of the set is a subgroup of G. So any subset of the normalizer which is a subgroup must be a subgroup of the normalizer. Okay, so this is one. And second, H itself is a subgroup of the normalizer of H, because for any H, for any little h in H, we always have H equal H by H inverse. This is always true. So both Q and H are subgroups of the normalizer, but the order of the normalizer of H divides the order of G, which is b to power alpha times m, and this implies that the normalizer, the order of the normalizer of H is in the form b to power, let's say, j times t, okay, some natural number t, okay, in order to divide this. And now, since q and h are both subgroups of the normalizer, and the order of q and order of h are b to power alpha, and alpha is the highest power, then this implies that the order of the normalizer of H must be b to power alpha times some natural number t. Okay, and therefore both Q and H must be a Sylow B subgroups of the normalizer, right? Because their order is b to power alpha is the highest order of the order of the normalizer. So Q and H are in fact is in the set of Sylow B subgroups of the normalizer of H. Okay, and now we apply Sylow's second theorem to deduct that Q and H are conjugates. Q and H are conjugates. So this implies that Q equal X H X inverse for some X in the normalizer of H. Okay, but now since this X is in the normalizer, we obtain that Q is X H X inverse, which is equal H, because X is in the normalizer. So we found that Q is in fact the same as H. So we started with the existence of one subgroup in S naught. We took another subgroup and then we found both are the same. And this means S naught contain only a single subgroup. Okay, so this means that S naught contains only Q. Okay, which implies that the size of S naught is 1. Okay, now we return to our lemma. Recall that the order of S is congruent to the order of S naught mod B. Okay, and we found that S naught equal 1, and this means that this size of S is congruent to 1 mod B. Okay, and therefore the size of S equal 1 plus k b for some integer k, and this completes the first part of this proof. Okay, because this is the number, the size of S is the number of Sylow B subgroups in G. Now for the second part of this proof, we want to show that n sub b, the number of Sylow p subgroups, in fact divides m, where of course the order of G is b to power alpha times m. Again, we will use group action, but this time we will use the action of G on S. So let G act on S, and S is the same, is a set of all Sylow. S is a set of all Sylow B subgroups in G. So act on S by conjugation. Okay. And now here is the interesting part. When we use action by conjugation, then we can call the Sylow's second theorem, where it says that all Sylow B subgroups are conjugate to each other. So by Sylow's second theorem, all Sylow P subgroups are conjugate. And this means if this is S, if this is a set of all Sylow B subgroups, and we have here our Sylow B subgroups, then the action by conjugation will create a single orbit. A single orbit will be created inside this set. And the reason is that if we take any particular Sylow B subgroup, then it can be connected to all other Sylow B subgroups by conjugation. And since this action is by conjugation, then the orbit must be only a single orbit. Okay. Now recall that the size of S, okay, is a sum of the size of all orbits. So if we take just a representative Q, one of the subgroups here of all orbits in S, but we have a single orbit. So this means that the size of S equal the size of this single orbit. We can take any subgroup Q, doesn't matter which one it is. So now by the orbit stabilizer theorem, this implies that the size of S, which is this one, is the index in G of the stabilizer of Q in G. Okay. And this now we are almost done, because since by Lagrange theorem, the order of G equal the index of the stabilizer of Q in G times the order of the stabilizer, okay, of Q. This is Lagrange's theorem, and this means this index in fact divides the order of G. So this implies that this index divides the order of G, and therefore the size of S divides the order of G. But the size of S is the number of Sylow B subgroups, so this one divides G. Okay. So this is the first step. So we have n sub b divides b to power alpha times m. But we also proved that n sub b is congruent to 1 mod b. Okay. And this means that n sub b and b are relatively prime, or in other words, n sub b cannot divide b. So it does not divide also any powers of b. And this leaves us with only one possibility, is that n sub b must divide m. And this completes the proof of Sylow's third theorem. Now let's conclude today's recording by taking an immediate result of Sylow's theorems. So if we have H being a Sylow P subgroup, then the following are equivalent. Okay, the following two things are equivalent. One, H is a unique Sylow P subgroup. In other words, this means n sub b equal 1. Okay, you have only one single Sylow P subgroup, and this is equivalent to H is normal in G. Okay, so these two things are equivalent, and this is very easy to see. If we have here, this is our set S, okay, of Sylow B subgroups, and what we have only a single Sylow B subgroup, but all Sylow B subgroups are conjugate. So this means if you take the conjugation, for example, if this is H, if you conjugate H by any element of G, so GH, G inverse, you are going to get H again because there is only single Sylow B subgroup, and this means that H must be normal in G. So we say that from 1 to 2 by Sylow's second theorem, okay, for all little g in G, we have H equal G H G inverse, and this implies that H must be normal in G. Okay, and the other direction is also clear. So if we start from H being normal in G, then this implies for all little g in G, we have H equal G H G inverse. But this means if we take any other Q assumed to be a Sylow B subgroup, then Q must be conjugate to H by the second Sylow's theorem. So this implies that Q equal X H X inverse for some X in G. But H is normal, so this implies that X H X inverse equal H, which means Q equal H. So there is always a single Sylow B subgroup in case H is normal. Okay, so this concludes now our proofs for the three Sylow theorems, and next time we will start doing some applications and results on Sylow theorems.